we talked about like symplectic form, but we started just symplectic form on R2N, which kind of standard form. And like although I essentially almost didn't pronounce this word, we thought about this. I defined symplectic form as just bilinear form, but of course I thought about this as a differential form because you could apply to vector pair of vector originated at any point. So you have a differential form, and this differential form, okay, in whatever kind of notation you have, but it's this form. This is a standard area form on the plane, and you have a kind of direct sum of the spot. So this so-called standard Darboux normal form for symplectic structure, and you can, as Dishan told yesterday, you can just define symplectic manifold as made out of these charts and glued by symplectomorphism, kind of preserving this form. Or there is a kind of like equivalent definition which said that this is just non-degenerate. It's a closed. So this is of course closed and non-degenerate in the sense that matrix is non-degenerate of this form, non-degenerate to form, which equivalent to, as ever we know, to the fact that volume form is not zero. And like Darboux theorem says that the every such form is locally like this. So globally, of course, not true, and even on R2N. Okay, so this is a symplectic form. So this symplectic form, if on R2N, of course, does not carry any kind of topological information, but in the case of, say, closed manifold, then to form, it's kind of like represent cohomology class, and this fact says that top degree of cohomology class is non-zero. So this is a give you restriction for closed manifolds to be symplectic. And you can ask, like, as you so you kind of deep into this topological. So as I said, that symplectic geometry appeared as some kind of language for mechanics, but now we kind of like, as mathematician, we took this and spoil everything, and kind of now asking question which nobody cared about, and so we just we said, okay, so what kind of natural for us mathematician question, which manifold could be symplectic, and then you have this immediately like formal property, or just tell such manifold, if it's closed case, it must carry cohomology class with this property. And also there is a condition on tangent bundle of manifold. It just says that if you drop the word closed, then should be at least non-closed form, and which means that, like, from the point of view of theory of just vector bundle, that means that structural group is reduced to symplectic group, and symplectic group is retracts to unitary group. So therefore, this is the same as from homotopical point of view as having almost complex structure. And moreover, you can always pick this almost complex structure in the way how I was telling yesterday. We can make this omega to be taming for this complex structure, means that it is positive form, positive on all complex direction. And you can even further you can make it even in some kind of almost scalar condition, even say, so it can sometimes called calibrated condition. We can say that you can find always for omega, you can find J such that omega is J invariant.
So for every symplectic manifold, closed symplectic manifold, we have almost complex structure?
Yeah. For give so symplectic, as I said, So this is a okay. So I don't really want to go into this direction, but just I want to say that like it's a piece of, say, linear algebra. So suppose you have a say symplectic form, standard symplectic form in R2n, and you're asking what is a space of all almost complex structure for which this is a kind of related by this condition, and then this is a so-called Siegel upper half space. So it okay, some generalization of upper half space, this one, and this is a contractible thing, and so therefore all compatible almost complex structure is a section of some bundle with contractible fibers, so it's self-contractible. So anyway, so always there exists a J, and over there's a contractible choice of this J. So that's why all the theory of the Gromov-Witten invariant kind of makes sense in this kind. Okay, but just again, I'm not going in this direction. So we have this the symplectic structure, and now we can ask, as I said, we can ask this question: which manifold are symplectic? And there exist, like from this point of view, there exist, of course, two necessary conditions, like existence in always case existence of this almost complex structure, or in closed case existence, and you can ask, are these conditions sufficient? Can you always find this? And well, it's known that in dimension 2 this is true. In dimension 4 it's wrong, and dimension starting from 6 nobody knows. So it's kind of amazingly open problem, which probably I would, if I need, okay, I don't, like there is no kind of like absolutely good reason for to think, but probably I would somewhat tends to say that probably this is true. So that always, so because probably every almost complex and almost symplectic in the sense manifold closed is symplectic. So if its manifold is not closed, that's the famous Gromov theorem, like which says indeed this is true. But in closed case, this is an open problem. So just kind of like at during one of exercises in this course, maybe you can answer this. Okay. So yes. So this when I kind of like I started thinking about all the symplectic manifold and kind of this thing, it kind of like, because I came so for some kind of topological side to the story, that was first thing which I was trying to prove, and of course I very quickly proved that this is the case, but turns out it's not quite true. Okay, so now this question has a relative version, even necessary. So that means, for instance, suppose you have a manifold with boundary, or even just ball. So I start with ball, and now you have a symplectic structure just given in the neighborhood. So it's a symplectic structure on some neighborhood. I use this Gromov notation. Op is just kind of, which means some neighborhood, not specified neighborhood, some kind of germ of neighborhood along the boundary. So you take a on the neighborhood of the ball, you have a symplectic structure, and you ask, is it possible to extend the symplectic structure to the ball? And again, there is a let's see what are necessary conditions in this sense. So it's one necessary condition that there is this almost complex structure which needs to be extendable, and of course, again, there is abstraction for this. But suppose it's extendable as an almost complex structure, and now what is a condition similar to cohomology class in this case? And condition just says the following thing. So, by the way, if dimension is equal to 2, then answer is always yes, right? So if you have an area form near the boundary, so area form is just essentially the same as a non-negative function, and so that it's always, of course, extendable. So the in 2 dimension is true, but now beginning from dimension 4, you have the following constraint, because if you consider omega restricted to the boundary or the neighborhood of the boundary, then because boundary is simply connected now, so then omega is exact. And because it's exact, then therefore you can like write Stokes theorem. So suppose you could extend. If you could extend that integral of omega like to the n, whatever it is equal omega n to the ball. So omega to the n is a d of theta wedge omega to the n minus 1, right? And therefore, this is the same that integral of omega of theta wedge omega to the n1 over the boundary. And so we know, therefore, and this integral, like if you change theta by any exact form, that integral will not change. And so therefore, form omega knows what would be the volume of extension. And clearly, it has to be positive in order to extend. And therefore, you have abstraction for extension. And again, you can ask this question where these 2 properties are sufficient. So you can ask this question, and then you can start asking all kind of parametric questions. So there is as I said, there is a Darboux theorem, and Darboux theorem said locally all symplectic forms are the same, and so in particular you cannot locally deform symplectics. There is no kind of moduli of symplectic form, and the same true according to like Moser theorem, kind of the same stability hold globally. So if m to n is a closed manifold, and now you have a family of 2. And now you need to add one more condition. You want to say that omega t just varies in the same cohomology class. So it's equal omega 0 plus some exact form. So if you vary this way, then all these omega t are equivalent, so there exists isotopy such that ft star of omega t is equal to omega 0, right? So there is no deformation of t. And the same true in the relative case. If you take a deformation of any symplectic form, and now you said fixed, say fixed on the boundary, say, then, well, in this case, of course, you also need to preservation of cohomology class, but in the case of ball, if you take any family of form fixed on the boundary, all of them equivalent. So you can ask 2 questions. First, is it true that given 2 form, symplectic form, which are the same on the boundary, on the ball, are they homotopic, which is the same as the isotopic? Are they equivalent? For instance, are there any non-standard symplectic form on the ball which kind of like is not homotopic to it? What? So you take a say ball, and on the ball you take a say form like omega 0 is a standard form, like this. You take a standard form, and then you take any other form, omega 1, such that omega 1 equal to omega 0 on the boundary. And you're asking, are these two forms are homotopic relative boundary, which means isotopic. So this is kind of one question. And
are you saying that you can reduce for question of arbitrary forms being homotopic to only checking this by dividing ball into?
so I am saying whether I can reduce question about any form to case 1 of the standard.
By triangulating.
Likely it's true, but I'm not sure. Okay. So okay, but let's consider this question, and then you can ask kind of like another question, whether suppose omega restricted to this neighborhood of dB is, let's say, potentially extendable. And by this I mean that it's extendable as an almost complex structure, and also this positivity condition met. So it's potentially extendable. Is it extendable? So you can ask. So the corollary of what I proved yesterday is the following. Corollary of our yesterday theorem about this case of for Arnold conjecture for torus, the corollary is that in any dimension, one of the things is whole, one of the things is wrong. At least one of 1 and 2 is wrong, meaning has a negative answer. So either there are kind of different form, non-homotopic, or there are non-extendable. Yeah. So this is kind of course, not very exciting, because like we know today that this statement always wrong. But nevertheless, let me explain you why.
So potentially extendable means that
Potentially extendable, that obvious abstraction vanishes.
Meaning there is an extension and it's unique. This statement is not.
Yeah, right. Yeah. So why is this? Because of course this thing. Yeah, maybe what?
That will imply that volume preserving and symplectic is like group as a group, it seems like same.
Yeah, so if it's true, yes. Yeah, but I think I slightly overstated what I can prove. Probably I indeed need to formulate this not just for the case of one form standard, but for any two forms which are equal to the bound. But anyway, let's see. So maybe what Deschamps suggested that he can. Okay, so maybe afternoon you prove that it's okay. Okay. So
If there is an obstruction, then we can't extend it.
if there is abstraction, then of course we cannot.
But then it is greater than 0.
No, you assume that there are no obstructions. These are soft obstructions. You assume they are.
Suppose this abstraction vanish.
Okay, we can change theta a bit so that it like vanishes.
No, I am saying, suppose you start with form on the boundary, and you know that this is positive, and form extend kind of as not necessarily closed form.
Okay.
So suppose in this case you could conclude, and yes.
Okay.
And so So there's again, I don't want to go very in this direction. That's kind of not so important, but I just want to mention this. Kind of, it's a, so the argument is essentially the same. So indeed, you can deduce from this that any volume preserving diffeomorphism can be approximated by symplectic, and we know that it's not true. And how we deduce it, we just kind of like we start doing this extension, take a triangulation small and start to do that, and applying these two things we can put. Okay, so if somebody interested in this, I can explain details maybe in the afternoon. Okay, so you have this. So, but by the way, so we know that 1 is wrong. What about 2? About 2, we know absolutely nothing. So in dimension 4, there exists somewhat positive result of Gromov, which says that every such form omega 1 is equivalent to the 1. So given such omega, then there exists isomorphism, some symplectomorphism between omega 1 and omega 0. But what we don't know about in this case, whether group of diffeomorphism of the ball fixed on the boundary, where this group is connected or not. This is open problem. And this problem is equivalent, in view of Gromov theorem, this problem is equivalent to this. It's exactly the same problem. The question, is a space, what is the space of such symplectic structure? Is it connected or not? And another question, what is a group of diffeomorphism? So in this case, it's a pure topological question, kind of this one. But in high dimension, we know absolutely nothing. We don't know. So it's kind of amazing that this is like so many years of symplectic topology, and this is one of like first question people ask at the very beginning, and we still have absolutely no idea whether it's true or not. So again, it's possible that there is some new idea needed, which maybe if you look at from proper point of view, that maybe. So just maybe somebody come and say, look at this, it's obvious that if you properly look at this. I was told by Gromov this story kind of this type, that was some seminar in IHS, and they were kind of like all extremely good mathematicians. They were kind of like they was discussing some work of Faulting's. And in this work of Faulting's was some statement, and it was written obvious. And they were all this seminar was kind of like discussing, and again was a Fields medalist, were all the extremely advanced people there in the audience, and they have no idea how this proved. And then some, again, I don't want to name the name, but some fresh person entered this one, and kind of like who was late for seminar, and he just listened and asked, what are you discussing? And said, well, we don't know, but this is obvious. And so indeed, so if you just, it's a statement, but you just need to look for it from right point of view. If you look from right point of view, this is it. So it's not necessarily mean that somebody kind of like write in paper something obvious and you have no idea why this is true. It's maybe you just have a completely, he and you have a completely different picture in the mind. Okay, so well, so let's kind of now move to the subject of my lecture. Let's move to this one. So let's consider like things which we call, it's called symplectic reduction. So So this is the following construction. So suppose you have a symplectic manifold, and then you have a inside you have a submanifold sigma, say, so say it has a dimension 2, and this has a dimension, say, 2n minus k, and k is less than n. So you have some submanifold of more than half dimension. And then this submanifold is called coisotropic. It's called coisotropic if you take a what is called omega orthogonal complement plane. So that means that all vectors which kind of like annihilated by form, so which annihilate T sigma. So this is then when this thing is contained inside T sigma. For instance, if you have a hypersurface, that every hypersurface automatically coisotropic, because then it's a orthogonal called one dimensional, and it's a direction of kernel always tangent. So like for half dimensional, although I didn't allow you to say less, but you can also say go in one dimension. This condition equivalent to be Lagrangian coisotropic, and then okay. So in this case, what is a like standard, like again exercise in linear algebra, that if you at every moment you have this kernel, which is a automatically k-dimensional subspace of the tangent space, then this plane field is integrable. So you get some foliation by this kernel of the generation, and if you consider any transverse slice to that, like here you have a transverse slice to what is called characteristic foliation to this one, then if you take a like holonomy along the leaf, just mapping, then it would, so the transverse slice automatically symplectic because you kill all kernel, and monodromy is preserving this transverse structure. So what you get, like in topology, you get foliation with transverse symplectic structure, right? Okay, so you get foliation with transverse symplectic structure. But sometimes this foliation with transverse symplectic structure happen to be fibration. It's just fiber bundle. So sometimes if you take a quotient, this T sigma, by this characteristic foliation, which I denote by F, then this is a not T sigma, but sigma itself, I quotient by characteristic foliation, then this happen to be some manifold symplective of dimension 2n minus 2k, right? This is a 2n minus k, and you kind of decrease by k, you get 2n minus 2k. So sometimes this happens. So let's call such coisotropic submanifold, I don't know, great, nice, good. Well, any good word. So you have such nice coisotropic submanifold, and now suppose you have such thing. And now, so we have now M. So what is the data? You have a M, and you have a sigma. This is kind of nice coisotropic. And now, in addition, suppose you have a Lagrangian inside M. So this is our sigma, and now this is our oh sorry, dangerous. And we have this our Lagrangian. And suppose this Lagrangian is transverse to sigma. So it's an intersect, kind of like maximal in generic way. And then you can take a L sigma, intersected L with sigma, and project it. So let's call this projection pi, and take this pi of L intersected sigma inside this W. So you intersect and project. And
Yes, I am confused with your picture. What is sigma in your picture? What is that? I thought sigma was like.
you have a sigma, and sigma is a coisotropic. Okay? And it has dimension 2n minus 2k. And it's kind of nice coisotropic. That means that if I consider its characteristic foliation, then this actually fibration. And now you, in addition, you have a Lagrangian submanifold in the space. So this is n-dimensional. And this n-dimensional submanifold, because it's transversally intersect, so this intersection has a dimension, what dimension? N minus k. It has the same codimension as this one, right? So you have a n minus k dimensional submanifold. And now and there is this projection to this W, which is a 2n minus 2k dimensional. And I can project via this projection, I can project it there. And the statement that this projection is Lagrangian in W. It has a half dimension there, and it is Lagrangian. It's not necessarily, it always immersion, but not necessarily embedding. It may have a self-intersection point. So the condition that it transverse ensures that projection non-singular, but it is a maybe immersion. So this construction is called symplectic reduction. So you intersect with nice coisotropic submanifold and project to the base. So the fact that it's Lagrangian is kind of straightforward. You can just immediately check.
So that condition, does that imply that the characteristic solution will be a fibration? That condition? I just don't understand.
So what condition?
That T sigma is
So
that is subset of T sigma.
So this is the definition of coisotropic.
Yes.
And this implies that our sigma is foliated.
Yes.
But foliation could be terrible, right? The space of leaf could be kind of very, very like some rep foliation, right? So it could be very, very complicated foliation, and the space of leaf is non-Hausdorff is really nothing interesting.
Yes.
But I assume, suppose it's not.
Oh, okay.
It's a big additional assumption. So kind of typical coisotropic submanifold is not like this. It's a kind of like this nice coisotropic submanifolds are rare and precious. So if you find one, just keep it and kind of. Okay, so now I consider I would need one very special case of this construction, and it's called Lagrangian correspondence. So Lagrangian correspondence in very particular case of this construction. So it has a Lagrangian correspondence. So you take any two symplectic manifolds, M1 omega 1 and M2 omega 2. Just any dimension. So this is 2n and this is 2m. And you take a product of this. Take a product of two symplectic manifold, and then suppose in this product you see Lagrangian submanifold. So it's a n plus m dimensional manifold, Lagrangian inside this product. Then So this such Lagrangian is called Lagrangian correspondence. So what are kind of example of this? So example of this is that you take any particular manifold and take a product it with itself, but with inverse thing, right? So then, if F is a symplectomorphism, then graph of F, as we already discussed, is Lagrangian submanifold there. And this is a particular good, nice example of Lagrangian correspondence. But it could be any Lagrangian manifold, not necessarily graphical. Okay, so you took this thing, take a Lagrangian submanifold, and now you can do the following construction. Using Lagrangian correspondence, you can choose any Lagrangian. Let's call it maybe okay. Let me call it lambda. You take a Lagrangian in this one, and using this construction, I will produce Lagrangian in this one. It will allow me kind of so not all one, but almost all. So what you do? So you take, so this is our product, and this is our Lagrangian, and this is a M1, and this is a M2. So you take this lambda, and take a product of lambda with M2. So lambda with M2 is a submanifold, and of course it's nice isotropic, right? Because exactly every lambda is characteristic direction, and this reduction is just projection to M2. And so you take this L, intersect with this thing. So you take L, intersect with this lambda cross M2, and project it lambda cross M2, yeah, and project it to M2. And for this, again, for this construction to work, we need this L to be transverse to this coisotropic. So it's not always true, but kind of like generically this is true.
And you need the foliation assumption.
But foliation assumption automatic, because in this case it's just fibration by this law. Okay. So conversely, of course, you can push forward Lagrangian from here there. So of course, in this example of graph of M, this is just, of course, image of Lagrangian. You take Lagrangian and take its image under symplectomorphism. Okay, so this is kind of very important construction, and all construction which we consider now will be special cases of this, of Lagrangian correspondence.
How is W equal to M2?
What?
Like the quotient thing, how is that M2?
Because my coisotropic manifold is a product of lambda with M2. And lambda is Lagrangian, so along lambda, so lambda is precisely direction of this kernel, so by quotient.
Lambda to be Lagrangian.
No, lambda is Lagrangian. Lambda is Lagrangian. Is this one.
I mean, you are actually when parametric family of Lagrangian now projects. There is a bigger Lagrangian that projects this parametric family.
What is parametric? I don't have any parametric.
M1 is a parameter. M2 is a parameter. M2 cross lambda.
But I don't want to okay, if you wish, of course you can think it as a parametric family, and parameter is M2 if you wish, but kind of I don't think it's a good point of view. Okay. Okay. So now let's consider two very special cases of this construction. So now what we So now, so we have a M1, M2. And suppose this M1 and M2, they are cotangent bundle of two other manifolds. N1 and this M2 is a cotangent bundle of an N2. Now, take any map. Take any map of N1 to N2, any smooth map. And with this smooth map, you associate the following Lagrangian. So you take a T star of, you take a, first of all, take N1 cross N2. And in 1 cross N2, you take a graph of F. So it's a set of points F of X. So it's a submanifold in this one. And now now you take a and now take a cotangent bundle of N1 cross N2, which of course is the same as a M1 cross M2, because it's a cotangent bundle of product is product cotangent bundle. So it's 1 M2, and now here, and now you have the following construction. So you have this N1 cross N2, and inside N1 cross S2, you said you have this graph, which is submanifold here. And for this submanifold, you take what is called is conormal bundle. So that means that at every point, you take in the fiber all form which annihilate this one. You take a submanifold, you take a all form which annihilate the submanifold. So this is automatically, so maybe I will write a mu star of gamma F. And this is a conormal bundle. And total space of this conormal bundle is Lagrangian, always. It always have a half dimension, doesn't matter what is it. This has a half dimension, and it is Lagrangian. So it's Lagrangian, and so now I apply now my construction to this. So now I have this M1 cross M2. Then you have this mu star of gamma F sit there, and this is for this Lagrangian correspondence, and hence it allows us to move Lagrangian from M1 to M2. Right? So there is the following kind of interesting fact, that you have any map, and any map between manifold allow you push forward Lagrangian for the cotangent bundle 1 to N1, but not necessarily all Lagrangian, but which are in transverse position with respect to this. But generically you can move them. Okay? And now I want to, out of this construction, I want to specify even further. So I want to consider two special cases of this construction, and the two special cases when F is inclusion. So F is just inclusion of submanifold into bigger manifold, or F, in the case B, F is a projection, is fiber bundle. F is a fibration. So, and each of this case kind of allow me to push them. And this, like, and both of them will be important, but like this is the most important for us case, and which leads this notion of generating function. So okay, I'll erase this. So now we start with any manifold and take okay, n, because it starts with some manifold, and take a cotangent bundle of this manifold, and I would like to study Lagrangian in this bundle. And I would like to have some kind of big class of Lagrangian submanifolds of this bundle. So there are some kind of like obvious nice class of submanifold when you take a graphical submanifold, right? So you take any, if it's a graphical, then it has to be graph of closed one form. But for today purposes, I kind of don't distinguish closed, non-closed. So you can either so you can think, say, n is simply connected or something like this. But anyway, so it's actually kind of important issue, but not kind of for our today. So I kind of do not emphasize this. So you take a Lagrange. So that's graphical. So given function on n, we get some LF, which is a Lagrangian and cotangent bundle. Right? But now I will define something which I call subgraphical. So I take some manifold, some manifold V, say, which is a fibration over n, is a fiber bundle over n. And now you take a function, and suppose you take a function V on R. Then this gives me LF. It gives me LF, which sits in cotangent bundle of V. But previous construction give me push forward of this one, so I get this P star of LF, which is Lagrangian, maybe with self-intersection. Again, provided some genericity condition, which kind of not some transversality, but with the same, you get P star of LF inside T star of V. And this one could be really, with topology pretty arbitrarily, it could be so you get this Lagrangian, and Lagrangian this type I will call subcritical, say, right?
So what is this LF? LF is a subset of T star.
LF
T star is just a graph of D of
LF is in T star of V. And I push forward it, and I get Lagrangian in T star of n. Okay, sorry, this is a kind of like, it's a two different worlds. Okay, you want me to do? Okay, that doesn't matter. So I'm just saying, do you have a manifold? If you have a fibration, you can push forward that you get a Lagrangian here. So this construct. So let's see what like formula like this one. So let's say, suppose there's some case that V is equal, just say, product. So this is a n times some fiber E, right? And then our function f is therefore function of two variables. And let's say call variable here q, and variable in the fiber, let's call it by letter eta. So f is a function of q and eta, right? And then what is the equation of this one? So here is our if you have this like PQ canonical coordinate, then P is equal df over dq, right, given. Where mean P1 is equal df over dq1, right? But here, this our Lagrangian, this subcritical Lagrangian, this P star of LF, is given by condition that. So how it's good? So first of all, how is given this LF in V? So there are variable. So like how we call it. So here you have a variable Q eta, the point here in Q eta, and in cotangent bundle like dual variable called P and I don't know. Maybe I don't want to eta. I think. Why do we need Greek letters? Like call it T, doesn't matter, and I call dual variable S. So you have a QT and PS. So like the form is PDQ plus SDT. Right? So then so I already see contradiction in what I wrote, but okay, I hope. Because you have P here, you have P here. Okay. Okay. So anyway, so you have this, and so you take a P is equal, of course, df over dq, and S is equal df over dt, like this one is given. But I need to restrict it to intersect with one, which precisely means so I have to enforce that Pf over dt is equal to 0 over this one. And so this is LF. So how you understand it? So F is a function of Q and T, right? But this is a system of equation, and T, there is as many T as a like dimension of the fiber, and here you have as many equations. So an assumption of transversality, this is actually means that this system is like locally solvable by implicit function theorem with respect to, you can express the T out of as a variable, and therefore plug here, and then this will be the equation inside cotangent bound of V in this one. Okay, so now why
What?
what
Potential of n.
it's inside of cotangent bound from N. So now why this? So I will stop in a few minutes. So now why do we why this is good? So if this is if I don't know, so I would like to kind of study some property of this Lagrangian in cotangent bound of N, and we notice the following thing: what are intersection of this P star of LF with zero section with N itself, with kind of zero section and cotangent bundle. So
T star.
what?
Do you mean T star?
Zero section.
No, but it's zero section, but yeah, intersection with. So this sits in T star of N, and N sits in T star of N as a zero section. So maybe I should write with 0, but kind of 0 N, zero section N, right? So you want to. So that means that in this system of equation, I also need to write that P is equal to 0, which means that that's a critical point of F. So therefore, intersection of the subgraphical Lagrangian with zero section are also critical point of F. So therefore, if I know more theory on this manifold and can control critical point, therefore I can control Lagrangian intersection of subgraphical Lagrangian, this idea. And of course, for this, I cannot do kind of like, unless I know some kind of behavior, something about the fiber, then I cannot say something. And so So that's what we'll discuss, and then
I'm
next
sorry,
one.
I'm confused. So it will be critical point if you restrict F to n, because V is product of n and E.
No. You push forward this Lagrangian.
Yes.
So you have so it's given by this system of equation.
Yes.
And now I am asking, what are intersection point of this push forward Lagrangian with zero section in n? And every point of intersection, a point where P also is zero. So it has to be global critical point of F.
Yeah, yeah. Because the second set of equations
yes.
also
Okay.
there.
And hence, if I kind of somehow know something about fiber, and maybe fiber not compact, I need to control behavior at infinity, then I can say something. Then that's what I'll say after break.
We can just take, so since you are only considering local equations, then we can just take V to be any like fiber, and then we can take the local trivializations to get the values.
Okay. Okay. She means that V need not be global product. You can perhaps do it.
No, we do, I mean, all this construction perfectly work for any fibration. So you don't need to be, yes, yes. But in fact, for our kind of application, like okay, this is also useful. So useful to consider general fibration. But for our immediate purposes, this would be sufficient to you. So I'm going to prove today some kind of theorem about what is called persistence of generating function, and like which would allow us to prove result using this theory. But first, I just need to slightly extend this kind of construction, and I need to move also not only to symplectic, to contact world. So now, if you have, I already mentioned today, there are contact manifolds. A contact manifold is a odd-dimensional manifold. Like at the first glance, it's something kind of like very much different from symplectic manifold, because it just instead of two form, you have just non-integrable plane field. And so what is symplectic there? But turns out that there is a following relation. So in symplectic, let's go first to symplectic world. So in symplectic world, if you have a, say, symplectic manifold, and in symplectic manifold you have some hypersurface, you have a odd-dimensional hypersurface. First, you have a symplectic manifold, and in symplectic manifold there are two kind of important vector field. So first, we already talked that this is a Hamiltonian vector field. So it's a vector field, and it's a kind of like general definition says that vector field. So if you take a like I will write contraction of omega, or like interior product of omega with V. So if you take like dual to V one form, then this is a differential of the function. Then such vector field called Hamiltonian vector field. So there are, of course, symplectic vector field also. It's a just slight generalization when we say this is a closed form, but not same. So this is so they characterized by the conditions that if I consider flow, or you can say Lie derivative of omega along V, then this Lie derivative is equal to 0, which equivalent to if you consider flow, then it preserves omega. So this is a Hamiltonian. But then there is another very important class of vector field which are called, so this is a Hamiltonian, but another very important class of vector field are called Liouville. So Liouville vector field means the following, that when you contract V with omega, then what you get is not exact form and not closed form, but in some sense just opposite. You get primitive form of omega. So that means that if you give a d of this, then we get back omega. And this is a equivalent just via kind of standard calculus of differential form that Lie derivative of omega along v is actually equal not to 0 but omega itself, which means that if I take a flow of v in the direction or along the trivial vector field, then we're just multiplying omega by e to the t. So this trivial vector field are symplectically rescale the form, but they also have this property, they leave Lagrangian, because kind of like symplectic structure remains the same. So they kind of like preserve all symplectic geometry, which is not kind of susceptible to like measurement. So kind of like, okay. So, but now suppose you have a hypersurface, and suppose you have a Liouville vector field which is transverse to this. Then, if you take this take this form v contracted with omega, say call it lambda, so this is the primitive of this. And if you restrict this form lambda to sigma, then turns out that lambda restricted to sigma is a what is called contact form. So if you have considered hyperplane on sigma, which is given by this equation, this hyperplane is a contact structure. So therefore, contact structure is what arises on transverse hypersurfaces to Liouville vector field in symplectic manifold. And conversely, this is also true. So if you take any so now you have abstractly any contact manifold. And now you would like to understand what is this corresponding how to relate this. I want to realize it as a hypersurface in some symplectic manifold transverse to Liouville vector field. So then what you do is the following. You take a cotangent bundle of the sigma. And cotangent bundle of the sigma has some canonical line field, which is just conormal to sigma. Right? I don't know how to write conormal star to sigma. So it consists of one form which annihilate xi. Like every hyperplane give me a line of form linear function which are 0 on this. So you get in cotangent bundle, you get this conormal, and total space of this conormal, let's call this maybe nxi. So it sits in cotangent bundle of C, and so this one has a dimension 2n, and this one has a dimension. Okay, we started with 2n minus 1, so this has a dimension 4n minus 2, and this one has a dimension 2n. Right? So you have this. The thing, and now I am asking, if this is a symplectic submanifold of cotangent bundle with the Peck economy or not? So answer, of course, not. Why? It never can be symplectic submanifold.
Not half dimension.
What?
It's not half dimension.
No, it doesn't matter how it could be. It's even dimension it could be. So why this cannot be like? Immediately you can say that whatever xi you take, this cannot be symplectic submanifold. There is some stupid reason. Which is what?
I mean, H2 could not be 0.
What?
H2 could be 0, right?
This
Yeah, but H2 is not good because it's non-compact. So no, you see, inside this n, you have sigma sitting itself, and it has a codimension 1. And our symplectic form of cotangent bundle on sigma is 0. So for it would have a codimension one isotropic submanifold, which is too much, right? And so this is not possible. But if you remove sigma, so you take instead of R bundle, you take a R star bundle. So you think about this as a R minus 0 bundle, then it could be symplectic. And turns out that it's symplectic if and only if this is a contact structure, right? So this bundle is called simplexization of Xi. So normally, so this bundle in principle could be non-trivial, right? It's non-trivial in case if sigma is not coorientable. But if so, it's not coorientable, non-trivial, so you cannot like split. But otherwise, if it's coorientable, bundle is trivial, and therefore this consists of two equal parts, like plus part and minus part. So if you say fixed coorientation, then as usually people do, we can consider instead of R bundle, we consider R plus bundle, and this is called simplexization. And if in the contact manifold we fix contact form, this contact form give me section in cotangent bundle and give me trivialization of this bundle. And so therefore, with respect to this trivialization, our form PDQ restricted to this like I write n plus sigma, whatever the thing, it will be just form S alpha, where S is parameter. So that's in most cases how people define simplexization. You said this is take a contact form, take a product with R plus, and take a form D of S alpha. It's called simplexization.
And how are you taking the conormal bundle there, because it has a submanifold?
You take a manifold, any manifold. Take a cotangent bundle of this manifold. Cotangent bundle of this manifold is symplectic manifold canonically.
Yes.
And if manifold itself has a codimension 1 plane field, this our contact structure, then you can take a line bundle which consists of conormal of this one, right?
Yes.
And so you get this n. And you can ask when this n is symplectic submanifold. And it is if and only if Xi is a contact structure, this hyperplane field.
And you were removing C from.
Yeah, removing 0, but otherwise, and actually even if it's cooriented, I'm removing half. Okay, so this is called simplexization, and this simplexization, so it's just kind of, you can think about simplexization as just product of R plus with sigma with symplectic form D of S alpha, right? If it have a fixed field. And then this vector field, like radial vector field, which so there is an action by scaling, but action by scaling, of course, scales symplectic form, and therefore this vector field S DODS, radial vector field along this one, is generate precisely Liouville, is a Liouville vector field. So what we get, that you get given symplectic manifold, you get this canonical simplexization, give this manifold times R plus. Our contact manifold sits there as some S equal 1 level set, and there is a Liouville vector field transverse to it. So this is a completely kind of equivalent reformulation. Now, all notions, like suppose you just learn symplectic geometry and you say, because I never heard about contact manifold. Then now you know everything about contact manifold, because all notions in contact geometry can be symplectized. So and this simplexization will be some notion in symplectization, which, well, either invariant with respect to the section or like equivariant with the section. For instance, so there are Lagrangian submanifolds which are conical, which the same product with this R plus, and they give us submanifold in contact manifold, and these submanifolds are Legendrian. So you can think about Legendrian submanifold as Lagrangian cone in symplectization. And you have a, for instance, you can consider contact vector field, which has vector field which preserve contact structure. And then you can say, well, what it is? Every such contact vector field lifts as a Hamiltonian vector field, and moreover, Hamiltonian vector field, which is like generated by Hamiltonian of degree 1 homogeneity with respect to this coordinate S. So kind of everything you can say and kind of reformulate it. And because of this, everything which I said about symplectic reduction now can be transformed into contact reduction. So, and how you do that, you just kind of, again, you say this in, you take, always you consider manifold with this some S plus action, with R plus action, and consider only object and submanifold which are invariant with this specific action. So, and then kind of like when you take a reduction, you preserve this invariance with respect to this action, and therefore you get again corresponding contact notion. So in particular outcome of this, if you have a, so there are two important contact manifolds with which we want to work. So one of this contact manifold is what is called one jet bundle of N. And this is just kind of, you can think that this is nothing else but cotangent bundle times R. So you take this thing, and if you have a canonical form PDQ there, you consider contact structure, well, plus or minus like the different convention, this form there. So maybe minus. I will write this. Yeah. I will write this. This is a contact form, and this gives me contact structure, and like DODZ vector field is a kind of contact vector field preserving the structure. So so this is one thing, and another important contact manifold is the one which give rise to the term contact, is called space of contact elements. It's a configuration space of non-holonomic mechanics. So if you take now any manifold sub n, and then you take for every point, you take a point of our space of contact manifold is tangent hyperplane, which is the same, what is a tangent hyperplane? Is the same as a projectivized cotangent bundle, right? Because up to it's a linear function, up to scaling, give me hyperplane. And sometimes people consider I write P plus T star, I consider co-oriented hyperplane, and this is mean projectivized by it only divided by positive scalar, right? So we have this projectivized cotangent bundle. This is another important contact manifold. Why this is a contact manifold? Because there is vector field like this. What is the contact structure there? Okay, contact structure. There is a P form PDQ, and form PDQ does not restrict to projectivization, but kernel of PDQ does, and therefore the kernel of PDQ defines this one, and this is precisely structure defined by this condition of skating. Okay, so this projectivized cotangent bundle, and kind of last thing which I would need, relationship between projectivized cotangent bundle and projectivized cotangent bundle and one jet space. So one jet space of n, of course, this has a dimension 2n plus 1, and this it cannot be the same because I have a dimension 2n minus 1. But now if I consider n cross r, so then this canonically sits there as a like open every dense subset, which is what? How you think? So you have a n, you have a n cross r, right? And now point of this one is a hyperplane, right? Tangent hyperplane. But let's consider tangent hyperplane which are not vertical. And every tangent hyperplane which is not vertical can be thought as a one jet, because it's precisely give me value of the function plus value of its differential, because this one. So therefore, this canonically sits there in this one, and this will be important for us. Okay. So you have the thing, and now I want to have some generating kind of like everything which I was talking about as generating function and so on, repeat here. So in particular, if you have a, so in one jet, so what are kind of most obvious Legendrian submanifold in these two manifolds? So again, if you have a function on manifold, then it gives me Legendrian there. I told you it give you Lagrangian and cotangent bundle, but if I just add value to take simultaneous graph of function and differential, then it will be one jet space, and this will be Legendrian there. And you can also talk about subgraphical thing. So that means that if you have a fibration over n, and if you have a function over this one, it gives me Legendrian in one jet space of n. How? It just gives me Lagrangian, but this Lagrangian you can add value to this function, you get Legendrian. So what is a kind of corresponding construction here? So here this, like if you think in this term, so what is a like corresponding object here, right? So you can function, when you have a function, is the same as a hypersurface, which is transverse to vertical direction. But now when you go to arbitrary, just whole PT star, not just this, we can consider any hypersurface. And any hypersurface have a conormal lift, like adding at every point tangent hyperplane, give me Legendrian submanifold, what is called conormal lift of the submanifold. So every hypersurface lift there. But then turns out that every hypersurface, if you take a fibration and you have a hypersurface in the total space of fibration, then it also gives me Legendrian submanifold there. It's called generating hypersurface. So how it does? So what it is? So suppose I have a, say, I take a plane. I take a R3 projected to plane, and I take some surface there sitting in R3. The question, what kind of Legendrian submanifold it generate inside R2, inside projectivized cotangent bundle of R2?
Can you repeat the question?
So every hypersurface give me inside projectivized cotangent bundle Legendrian, right? Which is kind of like. But now, if I take this hypersurface and I take some fibration over manifold, I take hypersurface upstairs, take their Legendrian and kind of push forward down, then I get some Legendrian in the base. But in this case, I take, for instance, sphere in R3, I project it to the plane, what it generate, what kind of Legendrian it generate in the plane.
Front should be kind of the Singularity set.
Singularity. You're exactly right. So what it is? What it is? You take this thing, and then it kind of projected, and it maybe will project as a smooth submanifold. Then the singular locus, the visible contour, will be precisely my genetic hypersurface. But generically, of course, you get some kind of fold, cusp point. You get some picture like this, and that will be Legendrian, which is projected there. So it's kind of interesting, like observation, that singularity of like projection of kind of hypersurfaces, like to the manifold, they are actually kind of similar to singularities of Legendrian, which we get. Okay. So let's now formulate kind of like main theorem, which I'll try to prove. We essentially proved it yesterday. So it will be, the proof will be just kind of retelling of what we did. So first, I want to define the following thing. So suppose you have a function on some manifold. So by quadratic stabilization, of this, I mean taking product of n with r and with some kind of big power k, and consider the function f and picking some non-degenerate quadratic form, you can like fix this. Okay, it doesn't matter, but to take non-degenerate quadratic form and there and consider function f plus q. So this function f plus q kind of direct sum. So it's this function of some whatever a variable here plus variable there, like f of x plus q of y is called quadratic stabilization of this one. So what we observe, that critical point of quadratic stabilization are exactly the same, right? So just because critical point of q is just 0, so it's kind of adding 0 to that. So it's then one-to-one correspondence. So now let's just consider the following thing. So you take manifold n cross some r with big dimension k, and suppose we have some function. Now we say function of this fx y. We consider function which is equal quadratic form and plus, I will write epsilon of xy, where epsilon of xy is a kind of the following thing. So either this is a function with, say, compact support, or I maybe not require the compact support, but this is a function which with bounded derivative at infinity. The function with bounded derivative at infinity, so any such function I will call function quadratic at infinity. Function which has the form, I call it quadratic at infinity. So it's not so important if it's a bounded derivative at infinity or just with compact support, because what is important, if I have a function with bounded derivative at infinity, then I can, if I multiply by slow decaying cutoff function, I will not create any critical point.
But you want derivative y to be bounded only, or what? And you are assuming compact.
And yeah, okay, yeah, in my application, yes. Suppose it's a closed menu. Yeah, but it doesn't matter. It's a because what is infinity? Yes. Okay. Yeah. Okay. So indeed, you're absolutely right. I will be applying it not actually to RAN, so I have to be a little bit careful. But okay. But main emphasis, say, if it's closed manifold, then this. So it's a function quadratic and infinite. So more precisely, you can say the following thing. So this what you want the following. So you want this function on this manifold n cross k to be what is called fibration of infinity. So you want this kind of to have some kind of compact part, and here it's kind of anything, but away from some compact end, this is just fibration, and here just there's a map over R. This is our function, and if we take a pre-image over some big n or minus n, in this end it will just honestly quadratic function, and here it's also honestly quadratic function. So you have a function like this. Okay. So here's a theorem. Now let f. So I formulate in several versions. So let f be, so you start from some function on manifold n, and LF. No, maybe I even start with the following thing. So take a cotangent bundle of n and take a zero section in n. And let LT and say t in some 0, 1 be a Hamiltonian isotopy of L0 equal to 0 section. You understand what isotopy? So Hamiltonian isotopy, you can either think this is a family of Lagrangian which remain exact, so that means form PDQ restricted at always exact, or there's an ambient Hamiltonian isotopy which kind of restrict to this one, and this is the equivalent thing. So you have Hamiltonian isotopy of L0, then there exists some big k, some kind of big number k, such that and family of function and the family of functions f t on family of function on n cross rk, which are quadratic at infinity, such that f0 is just equal some quadratic form, and ft generate generate LT. So then this actually kind of immediately implies all kind of like other versions. So you can say, well, suppose I started this isotopy not from zero section, but for graphical or maybe even subgraphical submanifold. Then after so it's already given on some fibration. And then you can multiply this fibration by RQ and quadratically stabilize it. And after that, deformation of the base can be defined as the deformation of lifted to deformation of function, generative function. And we can, in fact, formulate this even kind of like here, just one parametric deformation, could be multi-parametric deformation. You can formulate it as a certain Serre fibration property, but I will discuss it tomorrow in more details and we need it. Okay, this is the theorem. So exactly the same. So this statement can be lifted to Legendrian case. So instead of this, suppose you started with zero section in one jet space, and you're deforming this Legendrian via Legendrian isotopy, and then you have a covering homotopy after quadratic stabilization. Also, you can lift it to the case of generating hypersurfaces, but now I didn't define what does it mean to stabilize hypersurface. To stabilize hypersurface means the following thing. So you take so suppose you started with some manifold n, and then in this manifold n you have a hypersurface. You have a hypersurface, and what I just want, in fact, I want this hypersurface will be homologically trivial. It's not, you can do without it, but let's assume it's homologically trivial. So sigma divide our n. So you have a dividing hypersurface. And this dividing hypersurface is given by some equation f equal to 0, where f is some function on manifold. And then you can stabilize this function and then write hypersurface, kind of stabilized hypersurface, f plus q equal to 0. And then you get hypersurface in n cross rk. You get some kind of stabilized hypersurface there, and we call this hypersurface quadratic stabilization of this. And of course, under this projection, singularity of the projection will be exactly the same, because kind of like, for instance, you started with hypersurface, and what you get kind of some hypersurface upstairs, such that when you project to n, its singular locus will be exactly our original n. And therefore, it will be generate the same manifold. And so again, you have a lifting property after quadratic stabilization for hypersurfaces. And all the theorem kind of will follow immediately from one of this kind of very elementary argument. So it's the same theorem. Now, who are authors? Okay, like first, again, you can say it was a result of Conley-Zender, which have never talked about any hypersurfaces, but in some sense, as a Duchamp with the clay afternoon, they had this kind of like infinite dimensional version of this, kind of what they're doing. But then immediately after them, Chaperon kind of wrote some finite dimensional reduction of this one, which is essentially was this version with hypersurfaces. But then Laudenbach and Sakharov, they wrote some paper where they formally defined generating function and proved the theorem. Then what Laudenbach and Sakharov, they didn't realize the following thing, that what they struggle, there is some kind of very simple formula which you can, for this one, which you can do for Euclidean space, or for like torus, which was done by Chaperon. But they wanted to do it for general manifold, and therefore they took this general manifold and take a covering, and there was a lot of hard work to kind of patch this, and so it was a non-trivial theorem. And then came Chikhanov, who kind of did it in Legendrian case, and who realized that there is some very simple reduction from manifold to submanifold. And therefore the fact that any manifold embed to Rn already kind of allow to reduce general case of any manifold for Rn. Okay, so that's where it belongs. Okay, so let me try to actually prove this main theorem in this case. So how we prove it? So I prove it for the case of just our manifold is Rn. But then for the general case, we will reduce it by some kind of trivial argument.
So we have a comment. So your singularities can be so you take the projection of the surface.
Are you talking about generating hypersurfaces?
Yes.
Yeah, this is a completely kind of different story already. Yeah, so in general, the singularity, of course, a priori could be extremely complicated. Yes, yeah, but then there are some kind of like many various H principle which kind of allows you to simplify the singularity. But so we can, in fact, kind of in my last lecture, when I will be talking about this arborization, I will actually need some results, so we'll talk about this. Okay, but at the moment, the singularity kind of irrelevant. I will not be using any information about singularity.
So, I mean, that perhaps why you are using quadratic stabilization also, and that stabilization will not change the generic nature of the singularity, and that's why quadratic stabilization.
What kind of stabilization you would?
Yeah, of course, you have to preserve the critical point. So
Yeah,
you will
right.
require.
So I think it's pretty uniquely if you want to preserve critical point, not much more.
Okay.
And you want to control at infinity, then I think
Already.
almost kind of like uniquely. But indeed, we will be also using kind of some other behavior at infinity, which is also useful. What?
I think he wants to use Morse function, not the quadratic function.
Yes,
There
yes,
is
yes.
no critical point near it.
Yeah, that's right. No, at infinity you have no critical point. Okay, so let's repeat what we. So I will be. So here in this formulation, what I was claiming that there is a deformation for some big k. But at the moment, I will not be care how to construct this family of this function. So I only will try to construct function for time 1. So generating function for, like you have deformation, you deform for some time, and then you come for time 1, how to find this quadratically stabilized function for this time for one thing. So you have this. So you have this like Hamiltonian isotopy, let's call it LT. And this Hamiltonian isotopy was generated by some, let's call it symplectic Hamiltonian isotopy Phi of this R2n. So LT sits in T star of Rn, which is a R2n. And we started with zero section in T star of Rn.
Then what do you mean
yeah, you take a zero section in T star of Rn, which I think as a kind of standard R2n, right? You have it. And you have a Hamiltonian isotopy. And suppose just not to kind of to go on all this unnecessary kind of like nuances, let's suppose it's it compactly supported Hamiltonian isotopy. So I take Rn and I have a compactly supported Hamiltonian isotopy. And so that means that there is a globally defined, compactly supported Hamiltonian function which defines some flow, which depend on time and define. And I deform it during this isotopy T from 0 to 1, and I come in time 1. I came for some Lagrangian L1, and I want to construct this stabilized generating function for this. Right? So how I do this? So I repeat what I said yesterday. So I take my phi t, and I split this phi t to many small things. So I partition my interval for 1 over n, etc. So therefore, this my deformation phi 1, or let's say this at the last moment, I present it as a maybe bit. Okay, let it present it. Maybe I use different letter. It's some psi1, psi2, psi, and some capital K. So you have a composition of psi, and each psi is very small, close to identity. And now I again draw this picture, which slight variation of what I was drawing yesterday. So I started with my R2n, and in this R2n I have a zero section sitting there. Then I have a take a two copy. I take this R2n cross R2n, and in this product of two copies of R2n, I consider graph of F1. And here I consider symplectic for omega. Here I consider minus omega. Here again omega. So now I have a cross. And here I consider graph again minus omega omega. And here I consider graph of F2, etc. Okay? So you have a here you have a zero section, and here you have a graph of this one. And this graph of this one is very close to the diagonal. So let me call this diagonal double 1. So maybe this is number 0 component. This is number 1 bar. This is number 1. This is number 2 bar. I put bar to remember that I changed sign.
What are capital F1 and capital F2?
There is no F1. There is a psi1. Okay? So this gamma psi1 is very close to this delta 1 bar 1 diagonal, because I just lit one. So there exists two, again, the following Lagrangian. That takes this product of all these things. So now, how many factors here you have, right? You have 1, and then plus 2 times k capital. 2k plus 1 factor of this R2n. So kind of enormous manifold. Now you have the following Lagrangian. So you have a delta this 1 bar 1 times delta 2 by 2. You take this one and cross 0. You take 0 times product of this. So let me call this product, I call delta odd. And now I do here, I consider this diagonal. I take a delta 0, 1 bar, and then delta 1, 2 bar. So you get this product of diagonals, so you get two manifolds, 0 times delta odd and delta odd times 0 in the last factor. Delta even, yes, a delta even times this one, right? So you take a product of diagonal, 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 and then odd number, so I don't missing 1, I have 0, and this one. So you have a two Lagrangian plane. And this two Lagrangian plane intersect along n-dimensional subspace. What is this n-dimensional subspace?
The full diagonal.
It's not full diagonal, it's full diagonal of 0. It is 0 plus kind of like 0, 0 cross 0 cross 0 cross 0, kind of, right? So, yes. So you get full diagonal. And they across it's precisely intersection of the thing. So you have a two. So you have the following picture. So you have a like n-dimensional Lagrangian, kind of Rn, and there is a two Lagrangian which contain it, which and each of them is equal Rn times Rn times Rn times k capital. Right? So you have a one Lagrangian, have a Rn times in another one. So you have these two things. So notice that these two Lagrangians don't quite generate the whole space, kind of like there's an n left. So now I'm okay. So you take this thing, and now you kind of slightly modify it. So you have this one, but there is a let me call this gamma or gamma whatever odd whatever thing, where I change each diagonal by corresponding graph. So the 0 times gamma, or just gamma, right? 0 times gamma is a product of graphs, and this is a product of diagonal. So 0 times gamma, 0 times delta is sorry, I kind of we're going all the time, but I finish in a few minutes. So you take a, you take or when I do need to finish? So I still okay. Oh, good. Okay, so yeah, because I thought everybody was hungry. Okay, so you have this Lagrangian. So this is a non-linear Lagrangian, but it's very close to this linear plane. And you have a graph. It's a 0 times graph of the product, right? And you have this one. So now
product decomposed into
not the graph of the product, but product of graph. Okay. Yes. Okay. We have a product of graphs, gamma, which kind of the almost like the delta odd. So now I will present in what I'm interested. I'm interested in graph in just f of 0 section, right? F of 0 section, and f of 0 section as sitting in R to star n. And now my claim is the following. Where is this 0 section? It's the following thing. What?
Phi of 0.
Phi.
Yeah.
Phi of 0 section.
They're with you.
Yes.
They're
Okay.
not.
So you have this phi of 0 section, whatever, this composition of all this small thing. And just what generated? So I need to present it as some reduction of something. right? So now what I'm doing? So I clear. What?
You can feed the zero section to this Lagrangian and get using think of this Lagrangian as a Lagrangian correspondence. You can feed the zero section there, and the result would be.
Yeah, but I need some also coisotropic something.
Correct.
Yes, I need coisotropic. So what is this coisotropic thing? Right? And this coisotropic thing is the following. That yes. So you take the following Lagrangian. You take a Lagrangian times Lagrangian. So you take this, as a Lagrangian for this construction, you take the zero, take this delta even, delta even time 0, you take this one. Yes, let me see what I'm saying. You take a 0 times graph. You take a 0 times graph. Yeah, you take this one. No, just opposite. You take as a Lagrangian. You take our 0 times graph. Kind of this. This is our Lagrangian.
Can be the coisotropic, like zero.
No, this is Lagrangian.
And that can be the coisotropic.
What is it?
That's zero section cross del I odd. Del even cross zero section. That can be the coisotropic.
Yeah. So now it's a coisotropic thing with whatever I call it, sigma, or how I call it.
Sigma.
Okay. For the sigma, you take now. So you take a 0 times this graph, and now you take this delta even, no, delta odd. This is an analog of delta odd.
Yes.
This is delta odd, 0 to delta odd. But now you take a delta even. You take a delta even, but not cross 0 section. If I take a cross 0 section, I get Lagrangian. But I take a class that holds this R to N, right? Yes, hold this thing, right? And then I take this thing, and I intersect with this one, and consider reduction. And this reduction will be to R to N.
Yes.
And kind of like this, again, set theory, which we can discuss today, tell us this reduction precisely phi of L. Phi of 0 section. Right?
Phi of 0 section.
Yes. So this is this. But now the only thing to understand, so this is a kind of trivial. But there's a one subtle nuance. And this one subtle nuance that I want to present it as a generating function, right? And generating function has a very, very kind of like special reduction, right? Remember how we define generating function. In order to define generating function, like in this case. So first of all, what we want R to N times, we want to have some splitting. R to N times we want R to we want okay, I will say this T star of Rn. I want to have it, and times some R of bigger dimension, and I would like to have a Lagrangian in cotangent bundle of Rn times this, and after that take this reduction with 0. And where I see all these things, then I need to do the following thing. So look what we have. We have this Lagrangian 0 times delta odd and delta even times 0.
The T star n, right? Instead of Rn, the first copy, that line. Exactly, that one. T star Rn cross R to the power something. So that R, you're not looking at Rn, I guess, n. Because you're looking
I didn't write anything here special.
No, that I understand, but the first factor, T
Yes.
star Rn,
Yes.
it should be T star n, because that's the manifold you started.
No, we're
My manifold I started was Rn.
Oh, Rn.
My n was Rn.
Okay. But n was closed, so I was all the way.
Yeah, but n was closed. N was closed, but here I said I have something with compact support, which is kind of as good as a close.
I see.
Right? Okay. So let's imagine the following picture. So you have these two subspaces. So our whole space. What is the dimension of our whole space? Dimension of our whole symplectic space, as we know, there's a 2k plus 1 times 2, right? So something like that. 2 times 2k plus 1. Oh, n. 2k plus 1 times 2n. Yeah, 2k plus 1 times 2n. So you have this one. So now these two space also have a dimension. So this has a dimension kn, and this has a dimension kn and plus knn. What I'm saying, not k. It's nn. K capital N. K capital N. And this one also has dimension n. And this one has a dimension k n plus n. And so this is so you have this Rn, and there are two subspaces of dimension kn and kn, complementary to this one, intersecting, right? So now the whole space can be viewed as a T star of this Rn, T star of this Rn plus T star of this Rn plus this times this R of this k 2kn plus this one. And you need to, whereas this Rn, you need to think not as this factor, last factor, but this diagonal. So if you think about this diagonal, then we have our space, if you have a T star of Rn times Rkn. And now here you have our generating function. It will be function which quadratic with respect to this thing, with this variable, and it would produce us via symplectic reduction something of T star of Rn. So there's kind of like nuance with this construction that at the last moment you do this all the symplectic reduction, but you need to make a change of variable. You make a change of variable, changing the splitting, so in such a way that so our Rn is kind of not like this. It sits in the space, but it kind of sits different way. And we need to do some kind of linear change of coordinate to make it diagonal. And when we do that, we get a kind of like correct generating function. But anyway, but essence of the 4 in this construction, and everything else is just kind of change of coordinate just to this.
Just to clarify, the generating function is simply this zero section cross product of graphs, by difference of this and the Lagrangian.
Yeah, so each of this diagonal, remember, each of this diagonal is generated by product of coordinate. So the generating function is a product, is a direct sum of this quadratic of product, and plus this epsilon which given by extra perturbation of the thing.
So
What? Because we are not diagonal, we working with the graph.
so what will be L then?
What?
So what will be L then? L will be just zero section cross D star R cross R K
No, zero cross graph.
graph.
Zero cross product.
No, this is a, yeah, our yeah, Lagrangian.
For you, delta odd is the graph. Odd is always graph.
What?
For you, odd is always the graph.
No,
Right?
diagonal. Odd is.
Or
All always graph, right? All of, yeah, yeah. So Lagrangian is 0 times product.
Yeah.
Delta odd is this product of diagonals.
Yeah, delta is product of diagonal.
Gamma odd is the perturbed guy.
Yeah, but kind of but graph product of our perturbation of odd diagonal.
1 second. So delta odd is just diagonal, straight diagonal.
Delta of the straight diagonal.
Gamma odd is perturbed diagonals.
Gamma is perturbed diagonal. Yes, and so when you do this reduction, you take a so as a Lagrangian.
yeah. So what is the Lagrangian? What is the Lagrangian you're finally taking?
Yeah. Lagrangian I'm taking is a zero, so original zero section.
Zero section cross.
Cross all gammas. This is our Lagrangian,
Yes.
and then this even diagonal times last R2n.
Yes.
This is our coisotropic submanifold. So we intersect and project.
So basically, for the identity function, identity symplectomorphism, you generate the, because this is just a perturbation.
So from identity symplectomorphism, I get zero section again, but kind of in very strange form. Okay, so I actually can, I'll maybe what I do, I'll write tomorrow explicit formula for this quadratic function to see. Okay. It may be not so expiring, but okay. Yeah.
It's essentially the same idea as before, because if you have a little perturbation of the zero section, of course that's generated because it's exact d of f,
Yeah.
graphical. But then every Lagrangian you can write as graph over graph over graph over graph.
Yeah, it's exactly the same idea, the same proof, but kind of slightly differently interpreted.